Welcome to our Mapping as Knowing series lecture. And today's theme, continuing the theme of this program, where we've been trying to bring to you distinguished speakers who work at the frontiers of either new fields or old disciplines that are reimagining themselves and are pushing out into what we in cartographic maps often see as terra incognita. So we've had some fantastic talks in this series where we are looking at the use of science and technology to inform questions about culture, nature, and human nature. And I'm absolutely delighted today to introduce our speaker for today, Jack Hidary from Google X. Jack works on artificial intelligence and quantum computing at Alphabet Google X, and his work on AI has included investigation into the dynamics of the generalization of deep learning neural networks. And he, prior to starting to head the group, the AI group and the quantum computing group at Alphabet, Jack has had a long history as a tech entrepreneur, and he started very, very young as a tech entrepreneur. The first company he co-founded was EarthWeb. It was a company that was dedicated to the needs of tech professionals. So from a very young age, he was able to see and map where the frontier was in terms of helping new fields grow and thrive. And he led the company right from his inception to 3 rounds of investment and its IPO. So at this point, to many of you, this might sound like, oh yeah, this happens all the time. But this was quite a while ago when this was really quite revolutionary. And it was a real start for venture capital funding and investment and IPOs. And under his leadership, EarthWeb actually acquired another company that some of you might know about. It's called dice.com. And it's a website that connected users with IT positions and others. Again, so he's always been mapping the domain of information technology, helping professionals connect with each other. And at DICE, he also co-founded and led Vista Research. So in addition to providing cutting-edge tools for professionals, he also started a brand new research web platform for investment firms. So he's committed, as you can see, to building new kinds of community, connecting people across disciplines. And he has also been very active in philanthropy. He has received many industry awards and community awards and has been recognized as a global leader of tomorrow at the World Economic Forum at Davos. He serves on several boards, including the X Prize Foundation. And he runs his own philanthropic foundation, which is dedicated to medical oncology research and has supported work at many centers, including the Sloan Kettering Cancer Center and UCSF. And he's trying to move the field away from using radiation, as you can imagine, exploiting big data and genetics for finding new immunotherapies and cures. He studied at Columbia University and was awarded a Stanley Fellowship in Clinical Neuroscience at NIH. And while at NIH, he did research on the use of AI tools such as neural networks to model and analyze data in functional neuroimaging. So it's an absolute coup for us to have Jack visit here today and talk to us. And today he is going to be giving us a primer on what the future of quantum computing looks like. Jack, welcome.
Thank you, Priya. Thank you very much. Priya, thank you for having me. Thank you all for having me for this Franke lecture. It's an honor and privilege to come here and share these thoughts with you today. I see a lot of friends in the audience as well. Jeff Sonnenfeld, hi, Jeff. Many other Yale friends have come here, so it's great to see and share this with the community. Mapping is a theme that I've, I think, pursued now for many years. If you think about the oncology field, where we've set up a foundation to focus on that, mapping the genome, for example, is a critical factor. The general human genome has been mapped for a number of years, but mapping the genome of tumors is a whole other story. And so in keeping with that theme, the NIH set up something called the TCGA, the Cancer Genome Atlas. So if you're going to map something, you want to have an atlas with you. And TCGA has been a very successful program by the NIH to start mapping the genome mutational signature of many of the tumors out there, many of the indications in cancer out there, but we have so much more to go. And we think that AI, machine learning, can be one of the tools as we do that kind of mapping. Today, we're going to talk about a different kind of mapping, mapping the future of a very interesting technology. And I have the privilege of leading groups within Google X, within Alphabet X, that focus on AI. That's one of my research areas. But today, we're going to focus on the other research group which I have, which is in quantum computing. And quantum computing is a very interesting field which really has a very recent history compared to lots of other fields. It's younger than the AI field. We can trace the AI field back to 1943, specifically, a paper by McCulloch and Pitts, two neurophysiologists who wrote a paper saying, we're looking at the brain and we see these things called neurons, and they seem to be connected up in a web-like fashion, a kind of a nodal structure. And it seems that's what the brain is up to. It has a nodal structure. There's no CPU. There's no central processing unit. There's no memory unit, specific memory unit. It's kind of a distributed architecture. And could we model this with an artificial neuron? And they thought of really one of the first artificial neurons out there. And that was followed up by work in 1957 by Frank Rosenblatt with the perceptron, a bit of an enhancement of that. And we're here today in AI because of the work of those early pioneers. Well, as we'll see today, quantum computing has a much more recent history, but a very fascinating one as well. So with that, I want to start with this slide, which really speaks to the fact that there's 3 more quadrants that we haven't really mapped yet in the world of computation. The world of computation that all of us generally practice today, if you have your laptop or access to cloud or crunching stuff with AI, machine learning, or simply using a sheet or a worksheet or things like that, we're generally in that upper left quadrant you see. We have classical data, and we're crunching on a classical platform. And by classical in this sense, in terms of a platform or computational platform, I'm referring to things that are not using quantum mechanics. And so that's really where all of us generally exist. But there's 3 other quadrants that we're just beginning to map right now. We have a number of ringers in the audience. Doug Stone and others are experts here and come from the Yale Quantum Institute. And there's been a lot of activity, particularly at Yale. And Yale's been one of the foremost centers for breakthroughs in this particular area. So it's really exciting to be here, particularly. But when we think about taking classical information and crunching it on a quantum platform, we'll talk about that a little bit today. What does that mean? Quantum information on a classical platform, probably not as fruitful. And then, very tantalizingly, what if we had a quantum sensor yielding quantum information, and then instead of bringing that to a classical platform, bringing it to a quantum computer, and I'll give you an example of that. So we're really at the precipice of some different interesting mappings of computational space. I want to mention that we feel very strongly that not only is this a rich area for research and advancing the field, we also want to invest and work with universities like Yale in investing in the pipeline of graduates coming out and studying this area, particularly in the PhD programs. We found that many of the textbooks in the space, while very interesting, were written many years ago. When I say many years ago, I mean more than 5 years ago, because more than 5 years ago, we didn't know many of the things that we know today in quantum computing. Many of the recent breakthroughs at Yale are just one example of what you will not find in a textbook that's 10 or 17 years old. One of the main Bibles in the field is about 17, 18 years old. We all love this book. We call it Mike and Ike because of the 2 people who wrote it. But 17 years ago, they could not have known many of the things that we know today. So as a companion, as a complement to that, we've just recently put together this textbook, which we want feedback on, and partly why we're here is to gain feedback pre and post this area. And I won't go through the whole book now, but the point is it really provides some of the core rubric and framework for people who want to get in the field. And if you're from the CS area or you're from the physics area and you want to learn more about this particular field, we want to provide more and more materials. And so this book is part of it. We'll get that out there, but also we have a number of collaboratories. Collaboratory is a Python notebook. It's written in Python, but it's in the cloud. And so you can share it, and we have a number of Python notebooks now that we're sharing publicly and for free of some of the key quantum algorithms, so you can kind of get a feel in a simulator initially, not in an actual quantum computer, initially in a simulator of what these algorithms look like. And then eventually we'll probably open up access so you can actually run it on the actual quantum hardware. And a number of other companies, IBM included, Rigetti, have now opened up cloud access to their quantum processors, so you can start to test some of the stuff. One of the challenging areas, aspects of this field is that it kind of draws from so many other fields. And so typically, if one got into this field in the last 20, 30 years, one had a background in quantum mechanics, quantum information theory, computer science, and if you wanted to get on the hardware side of this business, you had to have a background in experimental physics. Well, the good news is tonight, in under 45 minutes, we'll skip all that. And we'll be able to jump right to the conclusion of how do we actually think about these things. But in all seriousness, it does take a bit of some of the knowledge in these 4 buckets if you want to have an understanding of what's going on in this field. But here's the good news. One does not have to become a deep expert per se in any one of these fields. This field really draws from all these different expertises. And in my group that I run, the research group, we have people from different disciplines all coming together. So that's really part of the answer of how do you actually manage all this area of knowledge. You can bring people with different expertises together and make that happen. I want to now kind of talk about and lay out quantum information sciences first. And so before we get to quantum computation, let's recognize that it's part of a larger structure called quantum information sciences. And at the very least, it includes quantum computing, which we'll focus on today, quantum sensing, a very interesting area that's yielding a lot of interesting breakthroughs today, and quantum communication. So quantum sensing, I'll give you an example of old quantum sensing and new quantum sensing. Well, if people have heard of an EEG, right, people know what an EEG is to look at brain waves. There's another way of sensing what the brain's activity is, and that's MEG, magnetoencephalography. So instead of electroencephalography, EEG, we have magnetoencephalography, and we know from physics that anytime you have an electric current moving, you're also creating a magnetic field around it. And so many years ago, about 38 years ago, people realized we can create a machine to detect very, very sensitively magnetic fields and the changes in those magnetic fields, and we can put a brain into that machine, and that's called an MEG scanner. And if you've seen an MEG scanner, it's quite large, because the quantum device that's being used for that is called a squid, and a squid has to be kept very, very cold. And so an MEG would take up most of the stage here, and you'd be fixed in the chair, and your head would be in this kind of funny contraption. And for about 30, 45 minutes, we'd kind of image your brain to figure out some of the brain activity that's going on, or perhaps in some cases of people not going on in their brain. And so MEG has been around for a while, but obviously very impractical in that sense. However, recently, using new kinds of quantum sensors, a number of labs around the world have created MEG-type machines that are portable. So they do not have to be kept very, very cold. And there's a cap, essentially. You can have lots of these quantum sensors all around your head, detecting with high sensitivity the magnetic field around your head that's generated in turn by the electric activity in our brains. And you can now walk around, do daily activities, and obviously that's a much more real world and better measurement of what's going on in that person's brain. So that's an example of a quantum sensor, and I'll show you another quantum sensor later on in this talk. Quantum communications is also a fascinating field that's really coming into its own right now. It's been known for many, many years that the quantum world affords us a different type of communications than we have traditionally. And the reason why this is now quite important today is because of the first bullet here, which is quantum computing. So we know from Peter Shor, and I'll discuss his proposal back in 1904 in a little bit, that we know that RSA cryptography is going to be broken one day by quantum computers. And RSA is what we use every day, all day, with our phones and our banking systems and going on Amazon and purchasing things on Amazon. This all uses RSA cryptography, a certain method of public key cryptography interaction. So when you bring up WhatsApp, for example, and it says, hey, this is end-to-end encrypted, that is using this kind of cryptography that Ravesh, Shamir, and Edelman came up with years ago. If you put a credit card into Amazon or other websites, it's also using that kind of technology. We know, though, that one day, we don't know exactly when that is, but we know one day quantum computers will be able to undermine that kind of technology. It can break the kind of keys that we use in that particular area. Now, that's years and years away. So why, you may ask, Jack, why are we thinking about it right now? Well, the reason is that large companies and governments who have huge pieces of infrastructure dependent on this kind of encryption can't wait till the year before this happens. They have to start thinking about these things right now to start preparing for that eventuality. The second reason is a lot of these kind of organizations are fearful of something called store now, decrypt later. So even though today it is not possible to crack one of these large keys, the fact is I can intercept your message, encrypted message, I can store it, and then years from now, I can decrypt it using one of these kinds of machines. And that is something that's happening today, right now, by governments around the world. And so this is not science fiction, this is not something in the future, this is happening right now. They're storing it now and will decrypt it years into the future. So if you're a government and you want to not have that happen, you have to start using other means of communications today so that your messages will not be crackable in the future once these machines become available. And so that becomes more urgent now if you think about it from that context. And so in a way, we have kind of a race going on around the world with lots of labs and companies and governments and others all involved in this particular area. So to kind of delve into this a little bit, we can see that what are the resources needed to make all this stuff happen? As you'll see in the main part of the talk on quantum computing, we're very far from a scaled quantum computer today. We're years and years away from a quantum computer that can do some of the things we really want to do with quantum computers. However, when it comes to quantum communications and quantum sensing, we're really right there right now. And so for quantum communications, we only have to manage a few qubits, and we'll describe what a qubit is. Only a few qubits we have to manage to make that system work. Now, the fact is, with quantum communications, as I'll describe, there's a few more pieces we want to make it global, but in terms of near distance and also satellite-based, we can do that today. And quantum sensing is also within our grasp today. There are many, many labs and companies around the world. There's even commercial companies producing commercial quantum sensing products today. So this is definitely within the realm of what's happening now, commercially available. On quantum computing, you can see that ultimately we'll need something in the 10 to the 6, 10 to the 7, 1, 10, maybe even 100 million qubits to do some of the things that we really want to make happen. We are far from that today, but it's very tantalizing to think about the implications of that. So just on communications for a moment, the Chinese have certainly a very robust program that is led by Pan Jianwei, and they sent up a satellite, the Misius satellite. Misius was an ancient Chinese scholar. They named it after him, and they sent up this satellite for about $700 million to send down an entangled pair of photons. So one photon went to this ground station, one photon to that ground station, and they sent down about 6 million photons an hour, and one pair an hour on average got to those ground stations still with their entanglement intact. And so when we think about quantum mechanics, there's just a few concepts. We don't, again, have to recapitulate all of quantum mechanics tonight, but what we can do is just think about a few of the concepts. And one of the concepts that this illustrates is the concept of entanglement. It's what Einstein was so enraged about when he called it spooky action at a distance. Many of the fathers of quantum mechanics actually were very unhappy about some of the implications of quantum mechanics itself. And we have to remember that some of the originators of quantum mechanics didn't start as quantum mechanics people, right? So Max Planck, he wrote his PhD thesis in the 1870s on thermodynamics. there was no quantum mechanics, obviously, at that time, because he had not yet invented it. And so when he realized, in what he calls, quote, an act of desperation, in the year 1900, that the solution to the so-called black body problem, this very, very, very puzzling issue, was that energy was quantized, came in buckets and units. It was not continuous the way we normally think about the world. It came in these little quanta, little packages from the Latin quantum, how much. And so when he realized that and initially gave his lecture in the year 1900 and wrote his paper in 1901, to his own surprise, this solved this major issue. But I have to tell you that for many, many years after that, he was very unhappy about the conclusion of his own work that he received the Nobel Prize for. And Einstein, again, very similarly, in 1905, wrote the paper that got him his Nobel Prize. He did not win his Nobel Prize for relativity, neither special nor general. He got his Nobel Prize for the photoelectric effect, for explaining that in 1905. And again, he took a page from Max Planck's 1901 paper and said, "Thank you, Max. I really appreciate what you did in explaining the black body problem. I now want to demonstrate that it's not just for that problem. It's a more generalizable solution that can now be applied to this very puzzling effect that if you have photons hitting a certain kind of surface, electrons pop out. And it depends on certain quantized natures of that light that is impinging upon that surface." And so this all now led to the understanding much later in a paper that Einstein wrote with Podolsky and Rosen in 1935 called the EPR paper, that we have something called entanglement. And like many different movements in the world, the initial thrust of this paper in 1935 called the EPR paper was to attack quantum mechanics, not to support it, but to attack it. And Einstein, Podolsky, and Rosen said, the logical implications, dear sirs, of the quantum mechanics that you have proposed is this crazy idea of spooky action at distance. Well, not only did they not topple quantum mechanics, it actually became part of the canon of quantum mechanics today. And so we know, and it's hard to kind of get our arms around it, but we know that it's possible to entangle two particles and then take them very, very far apart, and they still have some kind of correlation with each other. And so that's a very, very puzzling thing, but this is what the Chinese satellite is doing, and it's sending a message, a key distribution, so we call it QKD, quantum key distribution, and that's what it's doing. And it really set off a plethora of press around this, but it wasn't just in the popular press. The Chinese published this in the magazine Science, in the journal Nature, in the journal Physical Review of Letters, and this became something that we now believe the Chinese have actually done. They've actually managed to send two entangled photons down, maintain that entanglement in one out of approximately 6 million pairs that are sent down, and send messages using that particular methodology. So this is a very different way of communicating than we do today with just standard RSA keys. And so this is really an interesting milestone. We always knew this was possible. It goes years and years back to the 80s when we knew this was going to be possible on paper. But to demonstrate this at such long distances has been really interesting. The previous record was 143 kilometers, demonstrated in the Canary Islands years before this. So to now demonstrate this at 1,200 kilometers, and then more recently, they demonstrated across 7,600 kilometers from Beijing to Vienna, and realized that, yes, they can do that as well. So this has really opened up a lot of interest and thought in the whole area of quantum information sciences. So now let's go from quantum communication now to quantum computation. It's often thought that Richard Feynman was really the first person to propose the idea of a quantum computer. If one does some research, though, we can find out, though, actually, he was not the first. I do give a lot of credit to Richard Feynman for being one of the, since he was so famous, of course, at the time already, to being one of the people who really promulgated this idea and made it quite famous. But actually, it's a paper by Paul Benioff that actually really first spelled out, about 2 years before Richard Feynman's lecture, really the core elements of what today we would call quantum computation. 1 year later, Yuri Manin, in a book written in Russian initially, translated as The Computable and the Non-Computable, wrote 1 or 2 paragraphs, and actually I went online and on eBay, I found an original copy of his book in Russian, brought it and got it, and I went to some Russian physicist friends of mine, and we found the paragraph and we translated it, and it does indeed allude to the idea of quantum computation. But certainly, Benioff's paper really does spell out many of the key elements that you would need to think about how to build one of these. But nevertheless, we'll come back to Feynman now. And in a lecture that he gave in 1980 and then written up and published in 1981, he spelled out the idea that quantum computing could be quite interesting. And what his main point is that nature itself is not classical. Nature itself, at the fundamental core of it, is not Newtonian. We can use Newtonian mechanics in many, many practical ways. When we want to send up a rocket to the moon, send up a rocket to orbit, we can use the approximation of Newtonian mechanics. But if you actually wanted to understand the fundamental part of nature, you'd have to have a computational device that itself is not classical, that itself is leveraging the principles and built on the principles of quantum mechanics. And you might say to me, Jack, well, isn't every computer built in some sense with quantum mechanics? Because it's made of stuff, and stuff is driven by quantum mechanics. But that's quite different, as we'll see. And so we do credit Richard Feynman for certainly taking the idea that was generally in the air now, and then taking it out there, and certainly starting down a very interesting research area today. So to show this looks like gobbledygook. What is this? And I hope by the end of the lecture today, we'll have some sense of what this thing means. What this is a quantum circuit. It's a circuit diagram. We read it like a music sheet from left to right. The things that we see over there on the left side, those zeros are, and the lines, the wires that go from them are representative of the qubits and their evolution over this computational time. So we have a qubit, let's say qubit number 0 over there on the top left, and we're going to do some things to it. We're going to apply what we call operators to it, and it's going to change over time. So if it started in a 0 state and we applied the not operator to it, we're going to turn it into the 1 state. A 0 becomes a 1. A 1 becomes a 0. And so what we can do is have a series of operators that we apply to these little qubits, and we demonstrate that over time in this way. I want to show it now in a slightly different way, and over the course of the lecture, I'll be describing in more detail how we actually get this done. But this is kind of a bit of now a planar view, kind of a three-dimensional view. And those gray things on the left, and we'll come back to this same image later on in the talk, but just to kind of give a prelude of it, those things on the left are those same kind of qubits, but now we can see that rather just being in a line, they're kind of in a square, in a matrix. And you can see that we now apply a series of these operators, and they change over time through these different operations. So now I want to just emphasize one of the key differences between quantum computing and classical computing. If I were to show you the inside of a CPU, of a central processing unit, of any computer that's in this room, any mobile phone, any laptop, what you'd find is a central processing area, and particularly you'd find an arithmetic logic unit, an ALU, where we actually add and multiply and divide and things like that. And then you'd find buses, little wires that bring data in and out to the ALU, and you'd find memory storage areas, both short-term memory and then long-term memory farther away. And what happens is we shuttle the data in and out using the buses into this ALU, and we crunch the information in the central processing unit. Not so over here in quantum computing. We term this computation in place. That is, rather than having data that's moving around and computing over here and then bringing it over there, we do something quite different. I like to think of it like a potter's wheel. People may know that if you have a potter's wheel and you put a clump of clay on it, you're going to shape that clay right there on the potter's wheel into something like a vase, and then that clay becomes the vase itself. We didn't take it, we didn't bring it, we shaped it right on the potter's wheel itself. So this is kind of a different way of thinking of computation. We're not taking data to and from different memory storehouses. What we're doing is we're starting with a certain state of our qubits. Some are set to state 0, maybe some are set to state 1, and then we perform some operations, and then in the penultimate situation, we have a set of states based on all the operations we apply to those qubits, and we finally do this red thing over here, that is, we perform a measurement. And here's the second fundamental difference between quantum computing and classical computing. If I had a very large classical computer, and I called that a parallel computer, the parallelism typically comes from both within the chips themselves and then having multiple chips. I could say, let's say, for example, I wanted to take the numbers 1 to a billion, and I wanted to square all of them. The number 3 would turn into the number 9, the number 4 to the number 16, and so on and so forth. And I could have multiple chips, each taking a division of labor of that large task. And so I can say, in effect, I've parallelized this because I've asked one chip to do numbers 0 to 100, this chip to do 101 to 200, and so on and so forth. And the great thing about classical computing is, the advantage in classical computing is, I can get all the answers. All the answers of those squares can be in a big table, and I can look them up and have all the answers. In quantum computing, we have certain advantages, which I'll describe, but one of our disadvantages, one of the catches here, is that when we take a measurement, we do not find out the state of all of our qubits. We really can only get a sampling. And so what we actually have to do is really figure out and be very clever about when we set up this nice kind of clay, potter's wheel and clay, and this computation in place, we have to figure out right before measurement, this penultimate state, that before measurement, we want to know that we've set up the probability, and we can think of the probability as these like slopes in a mountain, these probabilities, such that the probability of getting the answer that we need is very, very high. And so this takes a lot of thinking about when we write algorithms. We can't just write them the old way. We have to write them in a very, very different way because of this unusual nature of quantum computing. So the regime that we're in right now, the era we're in right now, we term the NISQ regime. And John Preskill coined this term just about a year and a month ago today. And that just stands for noisy, intermediate scale quantum processing. What does that mean? Noisy means that it's not error corrected. Right now, the computer you have, the laptops, the mobile phones you have, they are error corrected computational devices. That is, if something jiggles, if something goes wrong in the computer and there's a bit of a corruption of the data, your computer will recognize that and will fix that, will recognize that. We also have error correction in communication lines today. If I transmit a message across the Atlantic Ocean and there's some corruption of the information, another computer at the other end will recognize that we have fault tolerance. We're able to say, you know what? It does not checksum. We have a way of recognizing that some problem happened, and it'll reconstruct the message and give the correct message across. That is not the case today in quantum computing. We do not have fault tolerance. And so we have the ideas of how we can do error correction. And here at Yale, there's some of the most fascinating work being done around the ideas of error correction. But we do not have a scaled computer today with millions and millions of qubits such that we can do error correction. Today, in most of the labs out there, we generally believe that we need about 1,000 of these physical qubits in order to get one fault-tolerant qubit. Now, there may be new breakthroughs happening right now, but let's just take that right now as a ratio, meaning that until we get to millions and millions of qubits, we can't have the thousands of fault-tolerant qubits that we really need. And so that's why John termed this noisy. Noisy is just another way of saying that it's not error-corrected, it's noisy, it can what we call decohere very easily. It's not coherent, it cannot maintain its state in a very, very easy way. The IS in NISQ is intermediate scale. What does he refer to there? He's referring to the regime we're in right now of having maybe 50 qubits to a few hundred, maybe 1,000 qubits. This is what we generally term to be intermediate scale. Once we're at 1 million qubits or 10 million qubits, we're going to be beyond this regime. But today, we're squarely in the noisy, that is, not error-corrected, intermediate scale, 50 plus or so qubits, quantum regime. So, should we lose all hope? Because we don't have a fault-tolerant computer, should we just stop working? No, we must go on, and we have some ideas that I'll share with you today about what we can do with these kind of NISQ regime devices. So first, let's talk about the qubit itself. What is kind of a qubit? Well, a bit I think we all have a good general sense of. A classical bit can be 1 or 0, and that was a great innovation that we owe to both Claude Shannon and Alan Turing and John von Neumann and the other pioneers of computing that helped us understand that this kind of digital representation of information would be quite amenable to the things that we want to compute. And so that's been a very successful program, and that will go on for many, many years. I want to say right now that quantum computing is not here to replace classical computing. We're not going to start running Excel spreadsheets on a quantum computer. We're not going to run our Little League kids' Little League program and roster on a quantum computer. So there's many, many applications for classical computers and supercomputers and things like that. But there are the kinds of things that quantum computers can do uniquely. And the way I think about quantum computers is as like a subroutine. So you'll have a hybridized system. You'll have a classical computer. Could be in the cloud. Could be a supercomputer cluster. Could be your laptop. And then you would subroutine out to the quantum computer those specific aspects that are best done by that kind of machine. So it's really kind of a minority of the cases of what you'd want to subroutine out, but those are very special things that the quantum computer can do. And so now we talked a bit about entanglement, which is so critical to quantum communications and also critical to quantum computing. But now we can also talk about superposition, another interesting concept that comes to us from quantum mechanics. And superposition is represented in part on my shirt, which, yes, I helped design. And this is a shirt with a cat. We don't like to say the cat is dead or alive. That's very sad. So this cat is awake, and this cat is sleeping. When we think about Schrodinger's cat, what Schrodinger was trying to say to us is that before we measure something, before we measure a system, it's really in an indeterminate state. In today's lecture, we're not going to go into the philosophy and implications of quantum mechanics. We can do a whole course on that if you'd like at some point in terms of Copenhagen School of Thought and other schools of thought. But let us just say for the purposes of this particular lecture that prior to measurement, we have something in an indeterminate state. It could be across a number, maybe an infinite number of different possible states. And each one of those possible states has a little coefficient, as we'll see. And that coefficient, that little number, if you square that number, gives you the probability that if you measured that state, that particular state would come out in the measurement. So if I had, say, the number 1 over square root of 2 right before the cat is awake state, and I had a 1 over square root of 2 over the cat is sleeping state, 1 over square root of 2, and I know this is a bit of math here, but we can all do it together, 1 over square root of 2 squared, so we'll take 1 over square root of 2, multiplied by itself, well, 1 times 1 is just 1, and if we take the square root of 2, multiply it by the square root of 2, what number do we get? Right, we get a 2. So 1 over 2 is a half. So by the principles that Max Born told us in 1926, we know that if we take the square of that coefficient, we call that coefficient an amplitude, we get the probability that that state will come out. In the case of the cat situation, we have a 50-50 chance of finding the cat awake or the cat sleeping. And we can apply that to many other areas. People don't realize sometimes it's not just a 50-50 thing. You can have many, many other possibilities. You can have 3 different states, 100 different states, 1,000,000 different states, and they can have different, they don't all have to have the same coefficient in front of them. They can have very different coefficients as well. And again, when you square that little number that's right before that state, you will find out the probability of when you do the measurement, okay, great, whether that state will come out or not. So what's interesting about a quantum bit, a qubit for short, Q-U-B-I-T, is that we can put these qubits into states of superposition. This is something that we cannot do in a classical computer. And because of that, we have a much larger computational space that we can handle rather than just the classical space that we normally have. And we'll now see some examples of that. What are some of the applications of this? So quantum chemistry is one very interesting application. This is a paper from some of my colleagues at Google thinking about how to think about quantum chemistry. When you think about the interactions of 2 atoms or 2 molecules and you want to figure things out, very often it's very difficult to do that in a classical computer. We can do approximations, but to really figure things out in a more exact way, one may be able to use a quantum computer. Cryptography, we've already had a discussion around how cryptography will be revolutionized to some extent as quantum computers become more powerful one day. We'll have to rethink cryptography itself. And so now let's talk about the actual innards of this ballgame. In classical world, we have these kinds of gates. We have, for example, a NAND gate. So I'm sure we can imagine what an AND gate is. An AND gate just says, this is the Boolean AND from George Boole, and then helped realized by Claude Shannon. To have an AND gate, we just say, if we have 2 bits coming in, we want to know what the output's going to be. And so in the AND world, if it's 0 in and 0 in on bit 1 and bit 2, then we'll have a 0 coming out. If it's a 0 and a 1, we still have a 0 coming out. A 1 and a 0, we still have a 0 coming out. Only when both are true, 1 and 1, do we have an AND say, yes, true, number 1 coming out. And a NAND, you can see, is just popping that all the other way. So a 0 and 0 will yield a 1, 0, 1, 1. And the interesting thing about a NAND gate that we find in classical computers is that we call it universal. You can build any kind of computational device in the classical world just building on different instances of a NAND gate. In practice, we use other kinds of gates as well. But this, you can imagine, is a simple logical Lego piece that we can build any kind of classical computational device. If you want to build a computer to do general office work or to crunch very interesting simulations in the world, you can build them all out of this one kind of gate, the NAND gate. And what we see in this world here, in the quantum world, that we can actually build them from different kinds of things. So now I give you an example here of what we call superposition. I know it's a bit of math on the screen, but don't worry, we're going to walk through it together. And so here I have two possible states of my qubit. I have a 0 and a 1 state. And before we get to measurement, we're going to put it into a state of superposition. And I mentioned to you before that I'll have a number called a coefficient or an amplitude right before each of those states. We can call the 0 state the cat awake state and the 1 state the cat asleep state. Whatever we want to say, if we have a spin of a certain kind of particle, we can have the spin this way and the spin that way. So that could be 0, 1, whatever we want to represent in this kind of two-level system. And we have the number in front of it. And again, if we square that number, as Max Born told us, we're going to get the probability that upon measuring this system, we're going to get the 0 state or the 1 state. So if it turned out that there's a 75% chance of getting the 0 state and only a 25% chance of the 1 state, that's what we might see after many, many repeated measurements. And so we can play around with this kind of idea, again, just called the superposition, really nothing more than that. We can also now have states of 2 qubits together, and we can represent them in this larger representation over here. And so now you can see what we were referring to before. We have the superposition of states over here, 0 and 1. I have my 1 over square root of 2. And now we're all mathematically together that if I just take that and multiply it by itself, I get the half. And a half is just 50-50 in this particular configuration here. We also notice, by the way, that the sum of the squares of these different coefficients here add up to 1. And that's because we're in a physical universe, and something has got to happen. And so either it's going to be this thing or that thing in this case. If it's a million possible states, one of those things will occur. So if you added up the square of the absolute value of all those particular possible states, we're going to get the number 1. And because these numbers, by the way, in this particular case, that's a real number, not a complex number, but it could be a complex number. Because of that, we can actually get these very interesting effects of interference, both constructive and destructive. And people here have heard of the double slit experiment. We are very in a conundrum. You send light through these 2 different slits, and there's this interference pattern. And that really results from some of the dynamics we're talking about here today. So we can think just very, very simply about these states here as column vectors. And the great thing about the mathematics of quantum computing, I want to assure you, is that the mathematics are simply about linear algebra. We don't need super advanced calculus. If you haven't studied multivariate calculus, don't worry. You don't need it for this. This is all about linear algebra and things like that. So let me just show a few things over here. And that I think will be of interest to this group here. So I talked before about the hybridization of computing. You can see the CPU on the left, and you can see the quantum computer on the right. This is one kind of quantum computer. There are many kinds of quantum computers out there. This is one kind. But you can see the hybrid nature of that we're going to have a CPU that's managing the whole process. And we can program that CPU using this kind of code here. This is Python code. So if you know Python or want to learn about Python, you can go online, learn about Python, and use Python code to control not only the CPU, the classical machine, but also control the supercomputer itself. And this is a very, very simple circuit that I just built over here. And this simply applies an operator. If you can see over here, there's an X over here. And that's an operator I'll talk about in a second. And then we apply measurement, and that's it. So this entire little piece of code, all it does is set up a circuit. The circuit I mentioned before is what we set up in quantum computers. It applies a certain operator, then it applies a measurement, and it gives an output. And interestingly enough, the output of a quantum computer is classical information. Not quantum information, but classical information. And so we can see that this is another example of what, if you went into a lab, what things might look like. This is a dilution fridge. This is from a lab at Lincoln Laboratories, and on the left over here, you can see that red thing over here, and that's keeping what's inside really, really cold. And point of fact, the temperature we keep these things at for this kind of quantum computing is about 7 millikelvin. So that's 7 thousandths of a degree above absolute zero. And so what's funny about this particular image over here is that it shows 4 Kelvin, that's 4 kind of degrees above absolute zero as the hot part, okay? That's the temperature of space. But the super cold part is at 7 millikelvin. This is an older diagram at 20 millikelvin. Now we typically do this at 7 millikelvin. And the technology behind the dilution fridge is also quite fascinating. And so that's how kind of it actually looks. I think it's helpful to see how it looks. This is another image of this type of superconducting qubit computer where you kind of like, many people call it a chandelier because it kind of looks like one. And the actual processor is not this thing. It's a tiny, tiny square that's right over here. A tiny, tiny square about this big that's just sitting right there and waiting for all this apparatus to get it super cold. And then another part of the apparatus you see there are the leads that are giving it pulses of microwave energy to kind of apply these operators that I was mentioning before. This is an example of some of the work being done at Yale right here. And a lot of breakthroughs are happening here. You'll notice that Rob and his colleagues here are standing around a dilution fridge setup in which is the superconducting qubit ballgame. But again, the work being done here has taken a new breakthrough approach, not similar to other work being done. And I commend you post this lecture to learn more about that. And this has now also been spun off in Quantum Circuits, Inc., a great startup that got funding that spun out of the lab here. But you can kind of see now in terms of how these things are set up. But let me emphasize, this is only one of the many ways to set up a quantum computing device and go from there. So let me now go here and talk a bit about some of the other applications. So Eddie Farhi and Hartmut Nevin wrote a paper just last year demonstrating that we might be able to run a QNN on a quantum computer, a quantum neural network. And so you might say, what is a quantum neural network? Well, we know what a neural network is. I mentioned early on at the opening of the talk that McCulloch and Pitts theorized that, hey, we should probably build an artificial network made of model neurons. And so now we've had a lot of success, particularly in the last 15 years, of building neural networks. And what Farhi and Nevin said, maybe we can build one on a quantum computer. Now, why would you want to do that? Well, it's probably not the case that you get any speed up on a quantum computer by performing a neural network on such a device. But what is the case, and this is what I want to show here, that you may want to actually run this with the output of a quantum sensor. And so this is an experiment. This is referring to an experiment for axion detection that's happening at Fermilab very shortly. In the next few months, they're going to turn on this particular detector looking for dark matter signals. And the output of that is from a quantum sensor. And so what Fermilab is doing, and we're collaborators in this particular effort, is to say, let's put a quantum computer down there with the actual experiment. And as the quantum sensor is sensing whether there has been or not been some kind of detection, let's actually process it with a quantum computer. And you can see, again, without going into detail, this is a quantum circuit. We now know that we read it left to right. We have a number of qubits. We have some operators on it that are operating on it. And so we can have this kind of circuit running on a quantum computer down there in the cavern with the actual quantum sensing device looking for dark matter itself. So this is, again, not something that's science fiction in the future. This is a project going on right now. And then let me just kind of show this graphic, which is kind of where we are and where we're going. So I mentioned a number of times that we're in the NISQ regime. This is the kind of 50 to a few hundred qubits that we see right over here. This is the near-term applications. Again, we can think about maybe neural networks for detection from a quantum device. We can think about quantum chemistry. We can think about other kinds of near-term applications, algos for NISQ regime processors. But ultimately, what we need to get is this, what we call useful error-corrected quantum computing area, which is over here when we have 1 million to 10 million to 100 million qubits. We're years away from that now, but what's very exciting is many, many groups, including here at Yale, are making great progress step by step by step towards this kind of future. So I do think now it's pretty clear to many of us in the field that this will happen. We don't know exactly how it happened. Maybe it'll happen with superconducting qubits or related types of applications and breakthroughs. Maybe it'll happen with trapped ions, with neutral atoms, with many other kinds of instantiations. Maybe several of these will be very successful, and I think that's actually probably the case. But whatever it is, once we get to that regime, many more things will become available to us than we have today. So with that, let me just conclude by saying that I think it's a very, very exciting time in quantum computing today. In general, in quantum information sciences, which includes quantum communication, quantum sensing, we're already seeing the benefits today from these kinds of technologies. And quantum computation certainly is in a very early phase right now, but one that is quite exciting. And so if you're thinking about a field of research to go into, it's certainly a great area to think about. If you're somebody who's just generally interested in quantum physics, in physics in general, and science in general, I think it's a great area to follow and to get more involved in, either as somebody who wants to get involved in one of the companies involved, and all those companies, and there's now about 50, as we track it, 50 venture-backed quantum companies out there. They all need marketing people and business people and operations people and things like that. So there's many, many jobs in these companies, not just research, that have to be done in these companies. So I think it's a very exciting area for a career as well. And let me just say that it's great to be with you here today. This is my email right here, hidary@google.com. And also one of my colleagues, Stefan. Please email me at any time to ask questions about what we're up to get involved with us at Google in terms of our particular programs, either as a student or as a collaborator, faculty, labs, things like that, or just to come and visit us in Mountain View. The weather is a little better than here, and we have very good food as well in our cafeterias, which I'm sure is famous now. So with that, thank you very much. Happy to take questions.
Thank you so much, Jack, for a riveting lecture and for a less brutalist version of Schrodinger's cat, right? There's always I like the awake and asleep rather than alive and dead. So I just want to thank here before we conclude and we have a reception outside and we step into the Q&A, Richard and Barbara Franke for the generous endowment that has made this lecture possible and the series possible. So we can open up to questions, and I think Ty has a roving mic. So go ahead.
We have a question in the middle there.
Thank you. Hi, thank you so much for your talk. With your background in tech entrepreneurship, where do you see the position of these large companies like Google, IBM, between startup companies like the VC-backed and the academic labs all approaching this? Where do you see that they're interacting, synergizing, and carving out different parts of the field? Yeah,
that's a great question. First of all, we need everybody in on this. We added up the total number of practitioners in this field. So if you think about, just to give you a sense of it, if you think about AI today, the field of AI, NeurIPS, which is one of the leading conferences for academic research in AI. This coming year now, 2019, Vancouver will be the gathering of NeurIPS in December in Vancouver. We'll have 14,500 people come to just one academic conference in AI. If we were to gather all the experts of quantum computing, so we'd have the Yale team, we'd have the QCI team here in New Haven, we'd have the Google teams, we'd have IBM, Rigetti, Microsoft. We'd have Delft in Amsterdam. We'd have a number of practitioners and experts in China. And let's say we gathered everyone we can think of. As far as we know, and we've actually wrote a list down, we think there's about 900 individuals at this point. Now, maybe there's more that are learning, that are coming up the field, that are getting PhDs soon, but let's call it about 1,000 human beings. So right now, the field is quite small when it comes to the actual practitioners and expertise in the field. And we think that it's really good news that venture capitalists have now woken up. Sequoia backed the Yale startup along with other really great investors. There's investors now in Israel. We just heard about Quantum Machines Inc. getting $5.5 million from some great investors there in Tel Aviv. There's investors on the West Coast who are backing a number of startups, including Rigetti, that's raised, I think, well over $100 million today. So I think the good news is that capital is starting to flow into the system. And most of those startups are really started by really good experts coming out of the top labs, right? So the Yale example is one, but there's other example as well coming out of top labs and spinning out. And so there's some real good depth in these startups. I think that we need more focus in the academic world. We're trying to do our part to encourage academic centers to invest in this. I'll give you one example. I came back from Australia a number of months ago where I went to visit 6 universities in Australia. 4 of the universities in Sydney, the University of New South Wales, known as UNSW, USyd, University of Sydney, UTS, and one other university are banding together in what's called the SQA, the Sydney Quantum Academy. What they recognize in Sydney is that each of those universities has a depth in one of the parts. I mentioned those 4 boxes early on in my talk today. One of the universities, UTS, is really good at the software side, at the algorithmic side, at the theory side. UNSW is really strong at the hardware experimental side. They've got really strong chops over there, and so on throughout those 4 universities. And so a PhD student applying in can come into any one of those 4 portals and then get advisors and courses from any of the 4 universities. And we're now going to contribute also pro bono our pedagogic materials into that consortium. So that's an example of what we really want to see happening, kind of an ecosystem. The AI ecosystem is very robust, very mature, is producing a huge amount of very interesting, tangible results. We need to grow the quantum ecosystem by many, many fold to get those kinds of results that we need. In terms of the big companies versus startups, I think, again, there's a lot of symbiosis and synergy to be had there. Do I believe that acquisitions will happen? I do. I think a number of very large companies have not chosen yet to be in this space. So there's a number of very large technical companies that we can all think of today that don't have quantum programs. I don't know why, but they don't have quantum programs. And I think that once they wake up and realize how exciting this space is, yes, it's a long-term marathon, not a sprint, but it's exciting. I think they'll wake up and say, you know what, it may be too late for us to start from scratch, building one by one a whole team. Let's go acquire one of these great venture-backed startups and bring that talent right into our company. So I would expect, and again, everything I'm saying here today is just my own speculation. This is not an official position of Google or Alphabet or anything like that. But my own speculation is that I think in the next 4 to 5 years, we're going to start seeing the M&A activity in the space. In terms of independent companies going public or things like that, I think we're many, many years away. I think the most probable route for these venture-backed startups is successful, healthy exits via acquisition from some of the large companies. And I think that's going to happen in a very robust manner. I also think the fact that the governments are now really involved. So the European Consortium, and the flagship, the quantum flagship in Europe is very strong. I just came back from the UK where they're pouring lots and lots of money into this area. The US has just passed a law and a budget towards this area as well in the quantum realm. So there's going to be money coming from the DOE and the NSF in these quantum hubs, $25 million a piece, $5 million for 5 years each. So I think the quantum hubs will start to generate more research and more training as well. And what I'm doing is really trying to go around to the leading universities of the world, such as Yale and Oxford and Cambridge and Imperial, I just came from in the UK, and engage with the universities and say, let's build a bridge between the university academic centers and the companies, and let's all work together to kind of get this ecosystem going. So thank you for that question. Other questions, please? Please, Doug. And maybe you want to say a few words about the center here.
Yeah, actually, I think what I want to say a few words about is just complementary to what you've said, because this is a lecture in humanities and science. And so, I think that probably the most important thing to get across was something you touched on, which is, why are we now talking about quantum? Didn't we do quantum 100 years ago? And didn't you tell me that lasers and transistors are all quantum? And what I would like to try to just give you the flavor of is what changed. Okay, so we understood how atoms worked, we understood how the nucleus worked, we understood how light was absorbed and emitted, and then we were able to build lasers using quantum mechanics. And in quantum mechanics, there are these very hard to visualize concepts of superposition and entanglement. And so we could figure out how nature worked, but it looked like all these features were actually impediments to human knowledge. And things were not in a definite state. You had to measure them, then you paired them the same way, they'd be in a different state. So that seems bad, not good for obtaining knowledge, not good for storing and processing information. And this thing here being correlated with something far away, and I measure one affects another, that also doesn't seem very useful. And it's the thing that Einstein did, in fact, fasten on as sort of a proof that philosophically there was a flaw in quantum mechanics. So the amazing revolution that happened pretty quickly at the end of the 80s and into the 90s is that now I urge you to use this phrase, which came out of Silicon Valley. We learned that this is not a bug, it's a feature. Okay, so this is really somehow actually a productive aspect of quantum theory that can be used to process information. It's not just an impediment to getting information about nature. Now, the problem is that when you try to do that, to maintain these quantum properties involves isolating things from the world to an incredible degree. That's why we cool them off to almost absolute zero and trap single ions and so on. So that's not something anybody thought was, a good way to make information technology. So no one was trying to do that until it was proven that if you could do that, you could solve problems or you could do unbreakable codes, things that in information science were really important. So that change, that sort of conceptual change, that superposition entanglement, the fully quantum features of quantum mechanics, which only previously were accessible for atoms and subatomic, are now becoming, through engineering, et cetera, available at a more macro level, and they can be used to process information. So that's an amazing revolution. This field absolutely did not exist when I went to graduate school. Nobody was going into quantum information. People knew there might be a Higgs. People knew there might be gravitational waves, but they did not know that there would be useful quantum computers. That's a completely revolutionary thing, probably the most surprising thing in low energy physics, or maybe in all of physics, in the last 60 years. So I do want to get that point across, and in complement to what you said, because it dovetails with.
Thank you very much, Doug. Thank you. No, it's really hard to overstate this revolution in understanding, and the fact that it went from just a theory to now practice in relatively short amounts of time. When you think about the time frames and time scales of science, is really quite exciting. So when I speak to PhD students right now in this field, they're literally in the midst of this ball game. At Google, we recently gave a course, a boot camp, a 3-day boot camp, training people in some of the concepts we talked about today. And so who showed up at this? Well, we have 100,000 people at Google, and a number of the people, I would say at least half the room, had degrees in physics from many, many years ago. So they were in school years ago, sometimes decades ago. And when they were in school, as Doug is alluding to, this was really not even on the horizon. And now, and at that time when they graduated, there were not many jobs for their particular specialty in physics, so they decided to learn some programming and come to Google. And now they could be at Google and do quantum mechanics. And this is kind of like the best of both worlds, being at a place with a lot of great free food and doing quantum mechanics at the same time. So very, very exciting.
So the question, so you alluded to the fact that quantum computing might not actually give us speed. Is that?
In some cases, yeah.
In some cases, right? So I wonder if you could speculate on what it is that quantum computing can give us beyond classical computing.
Sure.
So are there particular kinds of problems? So, so what I'm alluding to is that, when we have the sort of challenge of big data and you look at using machine learning or AI techniques currently available,
yeah.
you can come up with correspondences, but you're not able to come up with causal inference, right? So does quantum computing buy you something new there?
Yeah. No, Priya, I'm very happy you're asking this question because often in the popular press, there is the misimpression that quantum computers provide speed up all around. That is, no matter what you run on this quantum computer, it speeds it up. And so it's really good to elucidate this point. That is not the case. In fact, the majority of things run on a quantum computer will not give you any speed up. In fact, in today's quantum computers, it's going to slow you way down because it's very, very tedious to actually get this stuff to work right now, but it's early days. But I want to bring us back to two things. One, we do know of a number of kinds of problems that have certain structure, and this was key. And what Peter Shor, sitting in Bell Labs in 1994, realized, and if there were a Nobel Prize for computing, he would probably get one of these prizes because he really came up with a fascinating insight. And I do also want to give credit to the two inspirations of his insight, which was Daniel Simon in Simon's problem, which is a very interesting algorithm as well, and Bernstein-Vazirani, Umesh Bernstein and his student Ethan Bernstein came up with a very interesting algorithm as well. So if you take Bernstein-Vazirani and Daniel Simon, and you mix it in a blender with some additional spice and insight, you get Peter Shor's insight. And what Peter Shor realized is that this problem of trying to factor a very, very large number, right, which is at the heart of our encryption today, taking something that's 1,024 digits as an example, and finding P and Q, the two prime numbers that when multiplied together give us this, massive number, that actually that's the same kind of problem as finding what we call the period of a function. And this is an amazing result that was realized at the time. When I say a period of a function, what does that mean? It just means very, very simply that if I had some function and it gave you, based on some input, some output, and then at some point, as you got to certain multiples of that input, so if the number 3 gave you a certain output, and then 4, 5, and 6 gave you some other kind of crazy output, but 3, plus some number, let's say plus 5, every single time it was plus 5, so 8, and then 13, and so on and so forth, gave you the same output as number 3, so that's the period of that particular function as one example. That actually easier problem was the same as finding this very hard problem of factoring large numbers. So there's a particular structure that he was able to leverage in this particular way that we do encryption that allowed us to get what we call exponential speed up. I should also mention that Love Grover, who is another fascinating individual that in 1997 told us that if we do a certain kind of search, not all kinds of search, but certain kinds of search on a quantum computer, we won't get exponential speed up, but we get a very significant speed up nonetheless. And so that was another indicator to us that one day this is going to be a very, very interesting area to go into. So there are certain problems that we've now identified that if we run them on a quantum computer, not one of today, but one of the future, that future I was mentioning before with the million, 10 million, 100 million qubit future, that kind of future computer, we're going to get the speed up. But I do want to emphasize now, coming back to this, I know it's a little hard to see now, but we recall that we can have this mix and match of mapping these quadrants, right? Today, we all live in the CC world. We live in the classical data, classical computing world. We have classical data coming from a healthcare system and say the healthcare system of Yale, New Haven has 100,000 patients with diabetes. We can take that information and crunch it and say, given the blood glucose levels of these 100,000 patients, let's predict how they're going to do on this treatment versus that treatment, right? That is a classic machine learning problem where we take classical data from the Yale electronic medical record system and we apply it on a classical computational device, that is a laptop, and we come out with some conclusion thereof. What I want to suggest to us now is that in addition to the specific research we're doing in quantum computing, that is how to build these things and how to run some algorithms, let's now take a wider mapping, a wider view of computation overall. Let's start thinking about when we now have quantum sensors, which now we're in the era. So while in quantum computing we have to think in the future about quantum computing, we can think about quantum sensors today, and you can work on those today, and there are commercial companies today who are doing that. Maybe we should start marrying that with quantum processors so that we can retain this data in the quantum world and crunch it in that sense. So I think this is one of the most exciting things. It's not necessarily always about speed up, although that, again, the popular press would have you believe it's all about speed up. Yes, that is one interesting aspect of some of the problems that have certain kinds of structure that we can leverage. But this is quite exciting, that we can now think more broadly about computation in general. And I think this is something that we have not yet brought into our classrooms yet, into the world of commercial computing companies. This is just an emerging idea that's really just beginning now.
So we
Maybe
have time
just one
for,
or two?
Yeah, we have time for
Yeah.
one more question before.
Jeff?
Well, I don't want to hog it if somebody else had a thought in the back that
We can probably squeeze in two, but go ahead.
I
Yeah.
stole the front row seat, so I couldn't get the last question. Given that this is an integrative lecture with the humanities and the sciences, I was just wondering about social impact. As we learned, Robert Oppenheimer reminded us about the scientist knowing sin with responsibility for being on the frontiers of nuclear development. We learned it again with life sciences. We learned it with social media. In this space, what national security dangers are they? This is the #1 top priority at Skolkovo, the Potemkin-like village outside of Moscow. And elsewhere. And should we be worried in the university world about affiliations and what constraints there are on the use of this knowledge?
Well, Jeff, it's a great question. I think it would not be overstating the case to say that those entities, and those entities could be corporations, governments, so on and so forth, that have the ability to leverage quantum technologies are going to have significant power in the future. I think that's fair to say. Today, we have that same discussion with AI, right? We know that those entities that have invested in artificial intelligence technologies, algorithms, knowledge, expertise, have significant advantage in the marketplace. And so if you're a quantitative hedge fund, for example, in Greenwich, Connecticut, or in New York City, and you have access to not only just faster computational devices, but actually the differentiator there is these kinds of algorithms that we're talking about in the classical world, then you have an advantage literally in the marketplace, literally buying and selling stocks. In this particular area here, we are in early days, but let me say that the power afforded to those entities that have mastery, not only of quantum computation, but again, let me also again put it in the context of quantum information sciences, QIS, quantum communication, quantum sensing, quantum computation. These three legs, you can even add another leg of quantum simulation, but these 3 or 4 legs of the stool, this is something that I would urge if I were to advise any government, any entity, any organization, I would say this is on the order of importance, if not greater, than AI. Right? So while it's slower to ramp than AI, because AI did not need all this kind of hardware innovation, literally new physics that's happening here at Yale and other places, it needed really just algorithmic kind of crunching, and also was really helped by the video game industry, which has created our GPUs, our graphic processing units, not intentionally, but they created for video games, and now we use them for AI. So there was a trifecta of very interesting factors that drove where AI is today. Well, and that took since 1943, so that was no overnight success either. What I would say in the quantum world is that we can now that we know what happened in AI, now that we know what happened in these other fields, I can definitely say that these areas are of great importance to any organization. And from an ethics and responsibility point of view, the one thing I want to emphasize is democratizing the information. That is my number one concern right now. The reason why I spent my Christmas vacation, I don't know what you guys did over Christmas break this December, but what I did is spend 17 hours a day for 21 days writing the book that I showed you a title page of before. And we did 6 months of research before, and we're still writing even after that. And we're looking for feedback from places like this to finish it up and then publish it very soon. And the reason why we did that is this is a money-losing operation. It's not to make any money, but because we really feel strongly, and I feel strongly, that we must democratize this information. Right now, this information is not democratized. It is in the hands, unintentionally, of a few institutions, those institutions are gaining speed and things like that, and we are training many, many different PhDs and other graduate students as a whole, but I don't think it's enough right now. And I think that, Moscow certainly has realized that and is putting, the Chinese, I can tell you, have certainly realized this. And I showed a slide of what they're up to, and so they're pouring a huge amount not only into the technologies but into training as well. What I would say that is there are a number of centers of excellence in the U.S. and Europe, and as well as China and Russia, but I would say that we have not democratized information. The amount of knowledge one has to have to enter into this field right now, and the tools at hand are insufficient for the amount of knowledge that you really need. And so it's my hope that we can form a small part and play a small part in the next 5 years of making it way easier to get into this field. And not everyone has to go and become a Rob Shulkoff, right? Not everyone has to go and innovate and create some massive new kind of computer. But I think there's many, many other roles to play, in this field. So thank you for that. And again, thank you very much, everyone, for coming tonight. Thank you.